welcome to the deep dive. You, our listener, wanted to explore some truly fundamental questions, the kind that, well, keep us up at night. Where did everything come from?
Why is the universe the way it is? Big stuff.
Exactly. And there's this one book that kind of against all expectations became this huge worldwide phenomenon tackling these very things, Stephen Hawking's A Brief History of Time.
Yeah, it's actually amazing, isn't it, how many people grabbed a book about, cosmology.
It really is. So we're going to plunge into some of the core ideas from this book, including some of the really fascinating updates in later editions that touch on things like wormholes and even the possibility of time travel.
Well, sounds great. Let's do it.
So let's get started.
It really speaks to a deep human curiosity, doesn't it? This widespread interest in where we came from, cosmically speaking.
Definitely.
And Hawking, he starts off brilliantly by showing just how much our understanding has, evolved. Remember that story he tells?
Yeah.
About scientists giving the lecture.
Ah, yes. The one where he's like confidently laying out the solar system, the galaxy.
Mm-hmm.
And then this little old lady in the audience just completely pulls the rug out from under him, insists the Earth is flat.
Right. And rests on a giant tortoise.
Yeah. And then the punchline.
When the scientist, probably a bit, bemused,
Yeah.
asks what the tortoise is standing on.
She hits him with, "You're very clever, young man, very clever, but it's turtles all the way down."
It's perfect. Such a humorous way to show how persistent some ideas can be, even the seemingly outlandish ones.
And it kind of reminds us of those earlier, simpler ways people tried to picture the universe, like Ptolemy's model.
Exactly. The
Yeah.
Earth smack bang in the center.
Surrounded by all these like crystal spheres.
Uh-huh. And those little circles, the epicycles, to explain why planets seem to wander backwards sometimes.
Okay, let's unpack Ptolemy's model just for a second. It wasn't like completely useless, was it? I mean, it did sort of predict where things would be in the sky.
Well, yeah, that's fair. It did a decent job for its time, making predictions. But there were definitely nagging issues, things that made people start looking for alternatives eventually.
Like what? What were the main problems with it?
That's a good question. I mean, while it made predictions, they weren't always spot on. For instance, it had real trouble consistently explaining why the moon sometimes looks bigger or brighter. Ptolemy himself even sort of acknowledged some of these issues. And also, the model just got incredibly complicated.
All those spheres and epicycles.
Exactly. It became really cumbersome as astronomers made more and more observations. But, it stuck around for centuries.
Why so long?
Well, partly because it just fits so neatly with the prevailing philosophical views, and religious ones too. Earth at the center of creation made sense to people.
Right, until Copernicus came along.
Yeah, then in 1514, Copernicus suggests something much, much simpler, a heliocentric model.
Sun at the center.
Sun at the center, Earth and the other planets orbiting it. Apparently, he even circulated his first ideas anonymously.
Yeah.
Maybe worried about the reaction.
I can imagine. So here you've got this like more elegant, simpler model, but it still took ages to catch on, right? What really tips the scales? What was the key evidence?
Well, yeah, it definitely wasn't an overnight thing. Kepler helped a lot. He refined Copernicus's idea, showing the orbits weren't perfect circles, but actually ellipses.
Okay, that made the predictions more accurate.
Significantly more accurate, yeah. But maybe the real sort of smoking gun came from Galileo, early 17th century.
With his telescope.
Exactly. His new telescope let him see things nobody had seen before, like moons orbiting Jupiter.
So things definitely weren't orbiting the Earth.
Precisely. I mean, think about it. You've got these celestial bodies clearly orbiting something else. That's a powerful visual argument against the whole Earth-centered idea.
Yeah, you can see how that would shake things up.
So those observations, plus the sort of mathematical neatness of the sun-centered model that gradually led people to accept it, it was just simpler and fit the facts better.
Okay, so a move towards simplicity and better observations. Now, zooming way out, Hawking talks about the two huge pillars of modern physics: general relativity.
Gravity, the universe on the grand scale.
And quantum mechanics.
The really weird world of atoms, subatomic particles.
Right. But the big head scratcher is that these two incredibly successful theories, they just don't play nicely together.
That's the fundamental challenge, isn't it? At the heart of physics today,
Yeah.
both theories work incredibly well in their own areas.
Like spectacularly well.
Exactly. General relativity nails gravity. Planets, stars, galaxies, how space-time curves because of mass and energy. Quantum mechanics is amazing at describing the tiny stuff, matter and energy at the atomic level. But yeah, when you try to use both theories together, say for describing a black hole or the very, very beginning of the universe.
They give different answers, contradictory results.
Yeah, basically, they break down, which strongly suggests our understanding isn't complete yet. There's something missing.
And that's the search for a quantum theory of gravity.
That's the big quest. A unified theory that can bring these two frameworks together. It's a major theme in Hawking's book, actually.
It does make you wonder, though, how can we be confident about any of this? If our two best theories clash, how can we trust our reasoning about the universe? Hawking brings up Darwin, doesn't he? Natural selection.
Right, and it's a fascinating argument. The idea is that our ability to, reason and understand the world, it's been shaped by evolution.
Oh, so?
Well, over immense stretches of time, individuals who could better figure out their environment, find food, avoid predators, predict things they were more likely to survive.
Okay, survival advantage.
And pass on their genes, including the genes that contribute to intelligence and reasoning.
So the argument is that our brains, sort of fine-tuned by evolution, should be capable of grasping the fundamental rules of the universe.
In principle, yes. Even though, our discoveries could be used destructively, the fact that the universe itself seems orderly, seems to follow consistent laws, it suggests our reasoning isn't totally off base. It should be a valid tool in this search for a unified theory.
Okay, that makes some sense. It's a kind of evolutionary argument for scientific inquiry itself.
Precisely. Now, let's maybe shift gears a bit. From the very large and very small to something that feels more, everyday, motion and time.
Right. Aristotle's view was everything wants to be at rest, with Earth as the ultimate fixed point.
Yeah, he believed in a preferred natural state of rest, Earth at the center, unmoving. But then Newton came along and his laws just blew that apart.
Newton implied there's no absolute standard of rest.
Exactly. Motion is relative.
Okay, this always brings up that classic example for me. You're on a train, right? Moving smoothly. You toss a ping pong ball straight up. To you, inside the train, it just goes up and down.
Looks normal.
But someone standing beside the tracks sees the ball moving forward with the train as it goes up and down. So who's seeing the real motion?
And that's the core point. According to Newton, both observers are completely correct within their own frame of reference.
There's no absolute viewpoint, no single place in the universe that's truly still.
Nope. Motion is relative. Absolute position in space isn't definable. And this had huge implications, not just for space, but for time, too.
How so? I thought time was separate.
Well, both Aristotle and Newton believed in absolute time. The idea that a second is a second everywhere, for everyone, no matter how they're moving.
Yeah, that feels intuitive, like a universal clock ticking away.
It does feel intuitive. But, as Hawking explains, this whole picture got seriously challenged when scientists started looking really closely at light. The Michelson-Morley experiment was key here, wasn't it?
Right, they were trying to find the ether.
Exactly. This hypothetical substance they thought light waves must travel through, like sound needs air.
So they figured Earth must be moving through this ether, and the speed of light should look different depending on which way you measure it relative to that motion.
That was the expectation. They set up this really clever experiment to detect that difference.
But they found nothing.
Zip. Null result. No matter how they turned the equipment, the speed of light always measured the same.
Which must have been completely baffling at the time.
Oh, absolutely. A major puzzle. People tried various ways to patch up the old theories, but then in 1905, Einstein comes along with his theory of special relativity.
And he just got rid of the ether.
Basically, yeah. He said, look, we don't need the ether.
Yeah.
And more radically, the speed of light in a vacuum is constant for absolutely everyone, no matter how they're moving relative to the light source or each other.
Okay, that's a simple idea. But it has enormous consequences, right? Especially for time.
Huge consequences. Because if the speed of light is always the same for everyone, but different observers are moving relative to each other, well, the only way that can work is if they experience time differently.
So time isn't absolute after all. It slows down or speeds up depending on your motion.
Precisely. Time becomes relative to the observer. And it doesn't stop there. Space gets involved too.
How?
Well, think about it. Speed is distance divided by time. If different observers measure different times for the same event, and they both measure the same speed of light,
then they must also measure different distances.
Exactly. Space and time are intrinsically linked. They aren't separate things anymore. This led Einstein to the concept of a single, unified entity. four-dimensional space-time.
Okay. 4 dimensions, 3 of space like length, width, height,
Uh-huh.
and 1 of time, all woven together. That's still hard to visualize.
It definitely is. Our brains aren't really built for it. Hawking uses that analogy. Locating a point in a room needs 3 numbers coordinates.
Right, like XYZ or on Earth, latitude, longitude, altitude.
So for an event in space-time, you just need a 4th coordinate, time, to say where and when it happens.
Okay, mathematically it works, even if I can't picture it. Hawking mentions space-time diagrams.
Yeah, they're useful tools. Usually you draw time going upwards and 1 or 2 spatial dimensions horizontally. It helps visualize the relationships, even if it's a simplified picture.
And within this space-time idea, there's the concept of light cones, future and past.
Right. That comes directly from the speed of light being the ultimate speed limit.
Nothing goes faster.
Nothing. So take any event, a point in space-time. The future light cone is the region of space-time containing all the events that could possibly be influenced by that initial event.
Because the influence can't travel faster than light.
Exactly. And the past light cone is all the events in space-time that could possibly have influenced the initial event.
And anything outside those cones.
Is in what Hawking calls the elsewhere. It's causally disconnected. It can't affect and can't be affected by the event at the center of the cones.
That really changes how you think about cause and effect, especially over big distances. Like his example, if the sun suddenly just blinked out,
Yeah.
we wouldn't know for about 8 minutes.
Right. Exactly right. Because that event, the sun going out, is in our elsewhere until the light, or lack of it, actually reaches us, traveling at light speed.
So when we look up at the night sky at distant galaxies,
We're seeing them as they were potentially millions or billions of years ago. We're always looking into the past.
wow. Okay, so that's special relativity. But Einstein didn't stop there. He then tackled gravity, general relativity, 1915.
Right. He wanted to incorporate gravity into this new space-time framework. And his idea was revolutionary. Gravity isn't a force like Newton thought.
It's curvature.
It's the curvature of space-time itself, caused by the presence of mass and energy.
Okay, so the classic analogy, put a heavy bowling ball on a stretched rubber sheet.
It creates a dip, a curve.
And if you roll marbles nearby, they don't go straight, they curve towards the bowling ball, not because the ball is pulling them, but because they're following the curve in the sheet.
That's the gist of it, yeah. Objects, planets, stars, even light follows the straightest possible paths through this curved space-time. These paths are called geodesics.
Even light gets bent, even though it has no mass.
Yes, because it's following the curvature of space-time itself. This was a huge prediction of general relativity that gravity should bend light.
And that was tested during an eclipse.
Famously tested, yeah, in 1919. A British expedition observed starlight bending as it passed near the sun during a total solar eclipse. Seemed to confirm Einstein's prediction.
And that historical detail is fascinating, the British confirming a German theory right after World War I.
It is quite ironic, though, as Hawking points out, looking back at the actual data from 1919, maybe the results weren't quite as clear-cut as they seemed at the time.
Oh, really?
Ambiguous. But don't worry, the bending of light by gravity has been confirmed many, many times since then, with much higher precision. General relativity definitely got that right.
Okay. And general relativity also messes with time even more, doesn't it? The twins paradox.
Oh yeah, the twins paradox. Classic thought experiment. One twin stays on Earth, the other zooms off in a super-fast spaceship, travels around, comes back.
And the traveling twin is younger.
Yep. They've aged less than the twin who stayed put. It vividly shows that time isn't absolute. Your experience of time depends on your motion and on the strength of the gravity you're in.
So there's no single master clock for the universe.
No. Everyone, every observer, has their own personal measure of time. Their proper time, as it's called.
It's just wild to think about time being flexible like that. Okay, shifting gears again slightly. How do we actually know stuff about distant stars, their composition, how they're moving? We can't go there.
Light again. It's our main messenger from the cosmos. By analyzing the light specifically, the spectrum of light from a star, we can figure out a surprising amount.
Right, like how Newton used a prism to split sunlight into a rainbow.
Exactly. When you do that very precisely with starlight, you don't just see a smooth rainbow. You see dark lines, missing colors.
And those lines are like fingerprints.
Perfect analogy. Each chemical element absorbs light at very specific wavelengths, specific colors. So those dark lines tell you exactly which elements are present in the star's outer layers, its atmosphere.
Okay, so composition from the spectrum. What about motion?
That's where the Doppler effect comes in. You know how siren changes pitch? Higher when it's coming towards you, lower when it's moving away.
Sure.
Same thing happens with light waves. If a star or galaxy is moving away from us, its light waves get stretched out.
Longer wavelength towards the red end of the spectrum.
Exactly. That's called redshift. And it's moving towards us, the waves get squashed.
Shorter wavelength, blue shift.
Right. And this was huge. In the early 20th century, astronomers like Hubble started measuring the spectra of distant galaxies.
And found they were mostly redshifted.
Overwhelmingly redshifted. And crucially, the farther away a galaxy was, the greater its redshift. The faster it seemed to be moving away from us.
Which was the first really strong observational evidence that the whole universe is expanding.
That's it, a cornerstone of modern cosmology. But there was another huge piece of the puzzle, discovered almost by accident. The cosmic microwave background radiation, CMB.
Ah, yes. Penzias and Wilson, 1965. They were working with this big microwave antenna.
Trying to do radio astronomy, communications, satellite stuff. And they kept picking up this faint, annoying background hiss noise.
Coming from everywhere, no matter where they pointed the antenna. They even cleaned out pigeon droppings, thinking that might be it.
Yeah, they tried everything.
Yeah.
And this noise just wouldn't go away. Turned out they'd stumbled onto the afterglow of the Big Bang itself.
Incredible, just leftover heat from the creation of the universe.
Pretty much. What's amazing is that physicists like Gamow, Dick, Peoples had actually predicted this radiation decades earlier. They figured the very early universe must have been incredibly hot and dense, filled with light.
And as the universe expanded and cooled,
that light would have stretched redshifted massively until today it would look like very cold microwave radiation coming uniformly from all directions.
And that's exactly what Penzias and Wilson found.
It was incredibly strong support for the Big Bang theory.
Okay, so this brings us to the theoretical models based on the Big Bang, right? The Friedmann models.
Yes. Alexander Friedmann, back in the 1920s, actually found solutions to Einstein's general relativity equations that described an expanding universe.
Starting from with an infinitely dense point.
Basically, yes. These models suggest the universe began in an incredibly hot, dense state, the Big Bang, and has been expanding ever since.
And Hawking talks about different possibilities for the future based on these models, depending on how much stuff, how much matter and energy there is in the universe.
Right. It boils down to gravity versus expansion. If there's enough mass, enough gravity.
Gravity eventually wins, stops the expansion, and pulls everything back together. The big crunch.
That's one possibility.
I agree.
Or if there isn't enough mass, the expansion just goes on forever. The universe gets bigger and colder indefinitely.
And there's a sort of just right amount in the middle.
The critical density case, yeah, where the expansion continues forever but slows down, approaching zero speed over infinite time. The geometry of space in that case is flat, like Euclidean geometry. The other models imply curved space.
But all these Friedmann models point back to a beginning, a singularity.
Yes, a key feature is that if you run the clock backwards in these models, based purely on general relativity, you reach a point in the finite past where the density and the curvature of spacetime become infinite.
A singularity, where the laws of physics, as we know them, just break down.
Exactly. It suggests a definite beginning to time itself, at least as described by general relativity.
That idea, a universe with a definite beginning, wasn't the only game in town for a while, was it? There was the steady state theory.
Right. That was a major competitor for a couple of decades, proposed by Hoyle, Bondi, and Gold. That idea was that the universe, on the large scale, looks the same at all times and in all places.
But if it's expanding, wouldn't the density decrease over time?
That's where their key idea came in. They proposed that new matter was continuously being created out of nothing all throughout space, just enough to fill in the gaps as the galaxies moved apart, keeping the average density constant.
Always existing, always looking the same. It avoids the beginning problem.
It did. And it was an elegant idea in some ways. But observational evidence started piling up against it.
Like what?
Well, surveys of distant radio sources, like the ones done by Martin Ryle's group in Cambridge, seemed to show that the universe looked different in the past. There were more powerful radio galaxies further away, meaning earlier in time.
Which contradicts the always the same idea.
Right. But the real nail in the coffin for the steady-state theory was the discovery of the cosmic microwave background radiation.
The Big Bang afterglow.
Exactly. The CMB is direct evidence of a hot, dense early phase that the steady-state theory simply couldn't explain naturally.
Okay, so the evidence pointed strongly towards the beginning. And then Roger Penrose did some important theoretical work around the same time, mid-60s, about singularities.
Yes, Penrose used some very clever mathematical techniques, focusing on light cones and the fact that gravity, according to general relativity, is always attractive.
Yeah.
He showed that under quite general conditions, when a massive star collapses under its own gravity,
It forms a black hole.
it inevitably gets trapped within a region whose boundary shrinks down to zero size. It must form a singularity, a point of infinite density.
So singularities weren't just weird mathematical quirks of specific solutions. They were inevitable outcomes of gravitational collapse in general relativity.
That was the implication of his work. And Hawking mentions the irony, right? That he, Hawking, later collaborated with Penrose to apply similar techniques to the universe as a whole.
To prove there must have been a singularity at the Big Bang.
Yes, based on general relativity. But then later in his career, Hawking spent a lot of effort trying to show how quantum effects might actually remove that initial singularity.
Fascinating how science progresses. But that work with Penrose in 1970 was a big deal.
Huge. It mathematically demonstrated, based on the established theory of gravity, that the universe must have had a beginning in time.
A beginning where general relativity itself breaks down.
Precisely. Which again points to the need for something more complete. A theory that includes quantum mechanics to truly understand that very first moment.
So wow, you, our listener, have just journeyed with us all the way from, well, turtles and crystal spheres
All the way down.
to the expanding universe, curved space-time and the edge of quantum gravity. We've seen these massive shifts in understanding.
From a static Earth-centered view to this dynamic, expanding cosmos. From absolute space and time to this interwoven, flexible fabric of space-time.
And the realization that the familiar world is underpinned by the strange rules of quantum mechanics alongside Einstein's gravity, it's quite a ride.
It really is.
Yeah.
And these shifts, they completely change how we see reality and, our own place within it all.
So the learner, here's something to chew on. Think about the implications. A universe with a definite beginning. A universe governed by laws that seem somehow to allow for both predictable evolution and this deep inherent uncertainty at the quantum level. If our picture of the cosmos has changed so dramatically just in the last, say, half century or so, as covered in these early parts of Hawking's book, what's next?
Yeah, what could be the next fundamental shift? What
Yeah.
might future discoveries reveal?
Especially as we keep searching for that unified theory, what does it even mean for existence itself if the universe really did spring from a singularity or from whatever quantum fuzziness replaces it?
It's vast, isn't it? A fascinating landscape to ponder.
Indeed, the quest goes on.
Absolutely. An ongoing adventure. And these ideas we've touched on are really just crucial stepping stones on that amazing journey.